Now, the idea behind using symmetry in any model is to be able to reduce the size of the model. Whenever we think about finite element analysis, so far we only think about simple elements like trusses, because that's what we have been familiarized with. But what you have to understand is the truss is just one of the building blocks of a kind of element that can be used in finite element analysis. There are many more complicated elements which go right up to the third dimensional coordinate system. So looking at solids, for example. So as you keep going into more complicated elements and therefore into complicated problems, which are much bigger in size, then the size of the model starts becoming a bigger problem than you would have imagined at this stage. So let's consider modeling in finite elements an entire fuselage section. Now, I remember doing this for my PhD thesis, and when I started off, there was a topology optimization done analytically with number of equations which sort of reduced the fuselage to just equivalent stiffnesses throughout. So that was quite simple. And this was more a global analysis because I just wanted to predict what the entire fuselage in general under certain loading condition will do and where the stiffnesses should actually lie. But once you do a preliminary analysis, you have to go into details, and that's when you need to model each and every part of the fuselage, including a bolt and a nut that would be required. So what you start doing then is you start thinking of smarter ways of reducing the size of the model by picking up certain sections which may be either repeated or have the same loads or can be just assumed to be simpler in a form of idealization. So what I ended up doing in general is just let me show you a picture. So if I had a complete fuselage section which looked somewhat like this, and there were of course frames and a floor beam and all kinds of vertical stanchions, and these kind of things all were present in the model. So what I realized is that every section which lies between the stiffener, so if I had frames, so frame 1 and 2, these are basically repeating units throughout. And it was a 16-meter long fuselage. So if I'm considering 16-meter long and this is only half a meter, then if I can just model this section, how much better would it be in terms of computational accuracy and speed? So what I did is that I took out first a section which was just half a meter length. So this was a frame and this was another frame. Throughout, of course, it was all round. And then I realized, hey, that's also something we can reduce if it is completely symmetric. And in my case, it happened to be symmetric about this axis. That means the loads were all the same, and so was the geometry. So I could actually reduce it now to one side, half of the fuselage with the two frames on either side. So that was one of the ways of reducing the size of the model, and this was just done on the basis of symmetry. So symmetry can be of, first of all, two types, reflective and axisymmetric. We will first discuss reflective symmetry. Reflective symmetry and axisymmetry both are used for model size reduction. And what we want to look for in reflective symmetry particularly is the axis of reflection. And the axis of reflection should be common for both loads and boundary conditions. So we cannot make a part symmetric if the loads are non-symmetric. So that is something we really need to be careful about when we start designing or modeling something using finite element analysis. When we find the symmetry plane and we start reducing the size of our model, so for example in this case, when I reduce the size of the model here, I had to make sure that the symmetry planes where I cut off the model, there were certain constraints that were applied here such that the model behaves in a way that actually if it was a full fuselage section. And the same thing in these directions would be continuous. This was an equation, not symmetry condition, because you want it to be repeating units. So there are certain, when you replace a certain axis of symmetry, then you have to replace it by means of suitable constraints. So the constraints have to be suitably modified and the load themselves also have to be suitably modified. And that is something that we are going to deal with in the class today. So if you look at this particular picture, then you see I start with a rectangle. I'm not using any loads here or boundary conditions. I'm just doing it on the basis of geometry. If I imagine that all the constraints were the same and all the loads were the same on all sides, and I could start reducing this model in such a way that first I'm only remaining with this section. Then I can also find another section which says, okay, now I have these two parts here, and I find another axis of symmetry, so I can actually now get rid of this one. So what I'm left with is this section over here, and then I can say, okay, I can also make it symmetric about this, and I can remove that as well. Well, so there are different ways of going up to symmetry, but then whenever you remove a certain part, you have to replace it with suitable boundary conditions so that the model still behaves in the exact same way if the geometry was completely full. So that's just an introduction to reflective symmetry. Now what we want to do so far now is I want to teach you some particular symmetry kinds. So the first one was reflective and the second one is now axisymmetric. And in this case also what we end up doing is looking for a certain axis of symmetry. And in axisymmetry, symmetry in geometry and load is always about the axis of the body, or otherwise also known as the axis of revolution. So if we look at this cylinder here, and then in this cylinder we have the axis of rotation, which is basically this axis which is marked already. It is rotated about this axis to form. So if I had one line here at radius r and I rotated it, then I would end up with this entire cylinder as shown over here. So what we know now already is that if I am going to slice out a small section of this throughout from top to bottom, then I will get exactly a part out of it which was revolved about this axis, and that is actually right here. So this is a small section which is a planar section of the top view, and this can also represent the complete geometry when extruded out of plane. So if it is extruded towards you or away from you, then this is the geometry that can form the entire cylinder and then rotated. Okay, so these are this is the top. And what you need to do therefore now is to also ensure that you have axisymmetric boundary conditions. What's good about Abaqus is that it automatically applies axisymmetry and symmetry as long as you provide what is the axis of symmetry. And then you don't need to think about it, but therefore before going into the software, I want you to think about it and form some symmetry choices. Now before we go there, in the same way for this cylinder, I can find another sort of symmetry or axisymmetry which can be set up. If I look here to the right, then what I did is I made just a planar view of this from the side. So if I'm looking from this side, then I can see that, okay, I can divide it into half and I can get one section out of it, which is again planar, so it has no thickness. And once it would be rotated or revolved about this axis, it would form the entire cylinder. So both of these are basically elements that can be used for axisymmetric formulation of the exact same cylinder. So now you can imagine that if I started meshing this cylinder in 3D, then I would end up with I do not know how many thousands of solid elements. And if I wanted to move to this particular choice, then I would just have 2D elements, which would probably be somewhat like this. And in this way as well, in the same condition, we will have much less number of 2D elements, which would be much faster to solve. So that's the advantage of using symmetry in either case. So as a recap, for reflective symmetry, we want to use a model size reduction. We want to find out the axis of reflection. The axis of reflection should be the axis of reflection both for loads and boundary conditions. And once we start removing parts because of symmetry, we have to replace them with suitable constraints and suitably modified loads. And in axisymmetry, the axis of rotation or revolution is always the one that is the axis of axisymmetry. And you can therefore reduce the model most likely in this way. So the kind of examples that we generally get with axisymmetry are generally rotated or revolved objects, either solid or shell, but also rotated. As an example, let's pick a pressure vessel. So let's imagine that there's a pressure vessel, which is a shell. So it's complete. Of course, it's 3D. So I'm going to start with so we have here This is a shell, it's hollow, and if I just look at a cross-sectional view, it looks like this right here. It's a pressure vessel, so it has uniform internal pressure acting all around inside. So if I start looking at reflective symmetry first, then I will be able to only make it into half and a quarter, and then and then for axisymmetry I can actually reduce it to just the one section of it. That would be the planar section defining the thickness of the shell, which is actually shown over here. So by reflective symmetry with step 1 we get half of the section. Then when we do second one, that means we take, so this, in the first case this is the axis of symmetry, and in the second case this is the axis of symmetry, and we are able to reduce the size of the model from right here going into this one and then finally going into this one. Now after reflective symmetry is completed, we end up with this and go into axisymmetry. In case of axisymmetry, we have taken out a planar section. Just it's exactly the same as the one done for the previous example. That means right here we went from a cylinder to an to a planar section which is axisymmetric about the axis of revolution. So the good part about here is that you have the geometry is of course symmetric. That's quite clear, but so is the load that is acting, and that is quite important, and without this we cannot use any of the symmetry conditions, as we will see in some of the examples ahead. Axisymmetry will most likely not be used during the course, but it's always good to know that there is an option like this. So if you are going to model something yourself for a dream team or for some project that you're working on, then this option is now available to you.